and she was awarded the prize of the best oral presentation by the Young EFC at EUROCORR 2025 in September in Norway. And so, Federica, the floor is yours.
Thank you for the presentation. And the topic of my today presentation is working variables effect on sealing post-treatment of coatings produced by plasma electrolytic oxidation on the magnesium alloy AZ31. Let's start introducing the material I work with, that is the magnesium alloy AZ31, characterized by the presence of aluminum and zinc as main alloying elements. This alloy is characterized by great mechanical properties, for example, fatigue resistance, dampening capacitance, and so on. And for this reason, it is largely employed in the automotive, aerospace, and nautical fields. Unfortunately, the performance of components made of magnesium AZ31 is compromised by poor corrosion resistance. In particular, this alloy suffers localized corrosion, and pitting, stress corrosion cracking, or galvanic coupling phenomena could take place. For what concerns galvanic coupling, it could occur between the magnesium alloy and external metals, but it could also take place due to the presence of impurities, or even because of the presence of intrametallic precipitates within the alloy itself. Indeed, these precipitates behave as cathodic sites, leading to the localized corrosion of the surrounding anodic magnesium matrix. To improve the corrosion resistance of magnesium AZ31, it is possible to perform a surface treatment with the aim of producing a protective coating on the surface of the treated component. A possibility is to carry out plasma electrolytic oxidation named PEO. PEO consists in a high-voltage anodic oxidation that is performed on a metallic component which is immersed in an aqueous electrolytic solution, and the treatment is carried out under conditions of plasma discharge, which are achieved when the applied potential overcomes the breakdown potential of the oxide growing on the surface of the treated substrate. As a result of the PEO treatment, an oxide coating is produced on the surface of the treated component. Unfortunately, PEO coatings are characterized by a high level of porosity, and the formation of pores is intrinsically related to the occurrence of highly energetic discharges during the treatment itself. So it is quite difficult to completely avoid the formation of defects within a PEO layer. The presence of pores is of course detrimental in terms of corrosion resistance, since aggressive species can easily penetrate through them, reach the metallic substrate, and cause its corrosion. To solve this problem, it is possible to perform a sealing post-treatment with the aim of clogging the porosity of the PEO coating by precipitation of hydrated species. So a sealing post-treatment provides a physical barrier effect, which allows us to enhance the protective behavior of a PEO coating. This physical protective effect could be combined with a chemical effect simply by introducing corrosion inhibitors within the sealing bath. Such inhibitors remain contained within the sealed PEO coating or the post-unit and could be released in case of corrosion. So by combining a PEO treatment with a sealing post-treatment, it is possible to produce corrosion-resistant coatings. Let's move to the materials and methods, starting from the PEO parameters. I perform a potentiostatic multi-step process with a total duration of around 6 minutes. I work in alternate electrical regime, applying a waveform consisting of a duty cycle 60% anodic, 30% cathodic, with a cathodic peak having a magnitude equal to 7% the anodic value. And this duty cycle is applied with a frequency equal to 1000 Hz. For what concerns the chemical composition of the electrolytic bath, I work with an alkaline solution having a pH ranging between 30 and 30.5, mainly based on potassium hydroxide, with additional sodium metasilicate to favor the formation of a thick oxide layer, and glycerin to reduce the turbulences within the electrolytic bath, promoting the formation of a uniform coating. Concerning the sealing post-treatment, the PEO-coated samples are immersed in a solution containing zinc and sodium nitrite heated to 1995 Celsius degree. Different treatment time as well as different pH of the sealing bath are tested. During this phase, the in situ growth of magnesium hydroxide as well as the precipitation of zinc hydroxide and oxide take place, providing the physical barrier effect mentioned before. In order to evaluate also the possibility of a chemical protective effect, a set of sample undergoes to a second post-treatment phase, during which the still sample are immersed for 30 minutes in a solution containing sodium metavanadate heated up to 50 Celsius degree. During this second phase, the deposition of vanadate ions takes place, and vanadate ions are chemical corrosion inhibitors. Now we could start to comment the results, starting from the characterization of the PEO-coated samples. By looking at the SEM image, we could observe a morphology that is typical of PEO coatings, characterized by the presence of cracks, protuberances, and pores. Then, according to the results provided by EDS maps, we could note that elements coming from both the electrolytic solution, for example, potassium and silicon, as well as elements coming from the metallic substrate, mainly magnesium and aluminum, are present within the final oxide layer, meaning that all these elements were involved in the plasma discharge during the PEO treatment. Now let's introduce the first sealed sample, let's say the reference one, that is named PS30. This sample is produced by immersing the PEO-coated specimen into the nitrite-containing solution for 30 minutes. The solution is heated to 90-95 Celsius degree, and its pH is equal to 10. By looking at the SEM and EDS images, we could note that small lamellas, mainly containing zinc, are spread all over the oxide surface, and these zinc-containing precipitates successfully clog the porosity of the PEO coatings, providing a great sealing effect. Now let's consider the first working variable, that is pH. To evaluate the pH effect on the sealing post-treatment, different tests are carried out, keeping constant the treatment time, equal to 30 minutes, and the treatment temperature, 90-95 Celsius degree, while the pH is changed. In the first case, an initial bath solution pH equal to 7 is tested. And in this case, we could note that just a few zinc precipitates are present on the oxide surface, and moreover, the porosity is almost completely unaltered with respect to the one of the original PEO coating. So working at this pH, the sealing process is quite unsuccessful. In the second case, an initial pH of the solution equal to 9 is tested, and in this case, again, we observe the presence of small lamellas spread on the surface. And in this case, the sealing effect is enhanced with respect to the case of the more acidic solution. Finally, an initial pH equal to 11 is tested, and in this case, more numerous and larger lamellas having epital-like shapes are produced. And even in this case, a great sealing effect is obtained. So, it is observed that for increasing pH of the sealing bath, keeping constant all the other working variables, more numerous and larger precipitates are obtained, favoring a more enhanced sealing effect and then an increase in the corrosion resistance of the sealed coating. Moreover, in case of the most alkaline solution, the zinc precipitates that are produced are characterized by flower-like shapes. In order to understand the different morphologies that are obtained, it is useful to what occurs within the sealing bath during the pH adjustment. The pH adjustment is performed simply by the addition of a few drops of a sodium hydroxide concentrated solution. And by looking at the video, we could note that as soon as some drops of this solution are added to the sealing bath, some whitish precipitates are produced. And at the end of the pH adjustment procedure, when the stirring is stopped, a white precipitate and deposit is observed at the bottom of the beaker. Chemical composition of this deposit is analyzed through XRD test, and here in the slide, 2 diffractograms are reported. The upper one is related to a deposit produced in a solution having a pH equal to 9, while the lower one is related to a solution having a pH equal to 11. We could observe that in both the cases, the main constituents that are found are zinc oxide and sodium nitrite. However, there is a significant difference between them. Indeed, for a deposit produced in a solution having a pH equal to 9, even zinc hydroxide is found. In order to understand this difference, it is useful to analyze the reactions taking place within the sealing bath. First of all, of course, there is the dissociation of zinc nitrite into zinc and nitrite ions. Then, when the pH is adjusted and reaches value ranging between 8 and 9, zinc ions react, forming zinc hydroxide. But if the pH further increases, reaching value between 9 and 11, zinc hydroxide is almost completely converted into zinc oxide. This explains not only the difference between the two compositions observed in the diffractograms, but also the different morphologies observed for the sealed samples. Indeed, we have said that for increasing pH, the quantity of zinc hydroxide that is present on the surface of the sealed coating decreases, and on the other hand, the quantity of zinc oxide that is present increases. And zinc oxide is characterized by a pita-like shaped structure that is exactly the one observed for the most alkaline sealing bath. Another phenomenon that we have to take into account is the fact that for pH equal to 7 or even lower, the partial dissolution of the zinc-containing precipitates as well as of magnesium hydroxide structure could take place. And this explains why, in the case of the most acidic solution, the one with a pH equal to 7, precipitates are almost completely absent. Now we could introduce the second working variable that is considered, which is time. To evaluate the time effect, the duration of the sealing post-treatment is doubled and the PS60 sample is produced. By looking at the produced sample, we could note that even in this case, just few zinc-containing precipitates are present and pores are not clogged. So the sealing effect is negligible in this case. If we directly compare the morphology of the PS30 sample with the one obtained for the PS60 sample, it is evident that lamellas almost completely disappeared. But if now we compare this sample with the one produced after 30 minutes of immersion in the sealing bath, but working at a pH equal to 7, we could note that its morphology is quite similar to the one obtained for the PS60 sample. And this suggests us that the pH of the sealing bath decreases over time during the post-treatment. So we measure the pH of the sealing bath during the entire duration of the sealing post-treatment, and it is observed that the pH value continuously decreases, and in particular, after 30 minutes of treatment, it drops, reaching a final value at the end of the 1 hour post-treatment close to 7. As I said before, such low pH could cause a partial dissolution of the already existent precipitates, leading to an almost complete disappearance of the lamellas that already exist on the surface, and then to a loss of the sealing effect. The final variable that is considered is the performance of a second step during the post-treatment. So the PS30 sample is immersed for 30 minutes in a solution containing sodium metavanadate heated to 50 Celsius degree, and the PS metavanadate sample is produced. This sample is completely covered by large pita-like shaped precipitates containing both zinc and vanadium. Even in this case, the porosity of the original PEO coating is almost completely clogged, and a great sealing effect is obtained. To understand why the morphology changed from the one observed for the PS30 sample, characterized by the presence of small lamellas, to the one described for the PS metavanadate sample, we have to think about the temperature effect on the zinc precipitates. Indeed, when the PS30 sample is exposed for 30 minutes to a solution heated to 50 Celsius degree, zinc hydroxide precipitates are almost completely converted into zinc oxide structure, as confirmed also by means of XRD analysis. And as I said before, zinc oxide is characterized by pita structure that is the one observed for the PS metavanadate sample. Finally, let's briefly comment the electrochemical behavior of the specimen. And the electrochemical characterization is performed through potentiodynamic polarization test carried out in a chloride-containing solution at room temperature. First of all, we could appreciate an increase in the corrosion resistance when comparing the bare magnesium alloy with PEO-coated substrate. Indeed, the corrosion current density is reduced by 1 order of magnitude. And the protective effect of the PEO coating is further enhanced when sealing post-treatment are carried out. In particular, the best results are provided by PS30 sample, for which the corrosion current density is reduced by a further order of magnitude with respect to the case of PEO-coated specimen. Even electrochemical impedance spectroscopy tests are performed working under the same conditions used for potentiodynamic polarization analysis. And even in this case, we could note an increase in the corrosion resistance when comparing untreated AZ31 with PEO-coated samples. And again, we observe a further improvement in the polarization resistance when sealing post-treatment are carried out. In this case, the highest RP values are measured for PS30 and PS metavanadate samples. Finally, if we analyze the shapes of the Nyquist curve reported in the slide, we could distinguish two main behaviors. In case of PS60 and PS metavanadate sample, 3 capacitive loops are observed. Here in the slide, just 2 of them are clearly visible. And this corresponds to the presence of 3 RCP parallels within the equivalent electric circuit modeling the structure of the coatings. While for what concerns the other 3 types of samples, just 2 capacitive loops are present, and this of course corresponds to the presence of just 2 RCP parallels having a cascade configuration in the equivalent electric circuit. So, to conclude, it is observed that the performance of this sealing post-treatment effectively enhances the protective behavior of PEO coatings, providing a physical barrier effect which hinders the penetration of aggressive species through the defects of the PEO coatings. For what concerns the working variables effect on the sealing post-treatment, it is observed that by increasing the pH of the sealing bath, the formation of zinc oxide rather than zinc hydroxide precipitates is favored. These promote the formation of larger and pita-like precipitates that are able to better clog the porosity of the PEO coating, improving its corrosion-resistant effect. When longer sealing post-treatment are carried out, it is observed that the pH of the sealing bath is reduced, and this causes a partial dissolution of the already existent precipitates, causing a loss of the sealing effect. Finally, when the second step post-treatment is carried out, consisting in the deposition of metavanadate ions, these promote the formation of larger lamellas that are able to better close the porosity of the PEO coating, leading to an improvement in the RP values. Finally, I would like to add some future outlooks. I will perform a deeper analysis on the pH influence on the reaction taking place within the sealing bath, as well as on the structure of the growing zinc precipitates. I will perform a sealing post-treatment working at different sealing temperatures, and I will perform a longer electrochemical test, even working at higher chloride concentrations. So thank you all for your kind attention, and thank you also for inviting me to this webinar.
Thank you so much, Federica, for this nice talk. And so I suggest to open the discussion for 5 minutes. And so please, you can open your microphone and question.
If you prefer, you can also ask in the chat, of course.
Okay. Yes. No one, no. The expert in PEO. And why using zinc, Federica, has a sealing
It mainly depends on the fact that we want to reproduce what already studied for aluminum, because my first experiments were performed on aluminum alloys coating with PEO, and I perform LDH sealing that are mainly based on the use of zinc nitride. And let's say I'm curious to see if this type of sealing solution will be efficient also for the sealing of magnesium. Obviously, in this case, probably LDH structure are not obtained because differently from the case of aluminum, there are not trivalent metallic ions. But anyway, it seems to work.
Okay, thank you. And so there is a question in the chat. I'm sorry, but I missed the concentration of the sealing solution and the PO bath. Could you show them?
Oh yeah, probably I didn't report the right concentration and composition of the sealing bath, but it is 0.05 molar zinc nitrite. Sorry, the sealing bath or the PO bath?
Sealing solution.
Okay, 0.05 molar of zinc nitrite.
Okay, and PO bath too.
PO bath is 0.2 molar potassium hydroxide with addition of 10 grams of sodium metasilicate and 10 grams per liter of glycerin.
Thank you, Federica. Other question in thank you. No, okay. Yes, Leonardo. Yes, ask your question.
Federica, thanks for this nice talk. How do you start your coating formulation? Is it some sort of recipe you have in your own lab, or is it something you can rely on the literature, on the web to start to produce your first coatings?
I base my let's say my recipe for the PO bath on literature, and then I simply try to use a different concentration of all the reagents and to analyze which one works better for the specific magnesium alloy and for the purposes that in this case is to obtain a PO coating that is sufficiently thick to allow us to perform the sealing post-treatment.
Okay, great, thank you.
Other question in the chat is, are you trying to prepare sealing process in combination with ultrasonic bath?
No, no, I never tried it. Maybe I could.
Other question, are you sure the sealing happened and probably zinc just deposited on the surface?
It's a superficial sealing, that's true. It's not completely close the porosity, but the sealing effect on the surface of the sealing is present. Let's say.
Okay, thank you. And last one, I suggest, would it be better to use two-step sealing to avoid precipitation in the bulk? First bath, zinc nitrate, second alkaline to promote only precipitation in the pores.
Oh, okay. It's a good suggestion. Thank you.
Good suggestion. Raphael, last one. Do you think the petal-like deposit could increase adhesion in case of painting top layer?
In case of painting top layer?
Yeah, the idea was to, if you want to cover the PO by organic coatings in the last step, do you think that could be increased adhesion?
Okay, thank you. Thank you for all the suggestions.
Okay.